Today we're looking at the T formulae. Now these are based off the double angle formulae, which in turn are based off those compound angle formulae. Now the compound ones and the T formulae are both on your reference sheet. The ones that aren't are the double angle formulae. So let's start down here. The T formulae actually express sine theta, cos theta and tan theta as algebraic functions in T, hence why they're called the T formulae, where T is equal to the tan of half theta. Okay, so let's have a look at what's happening here. If we look at the double angle formulae, and we don't have these on our formula sheet, but we do have the compound angle ones that say, for example, sine of alpha plus beta, and so we can derive these ones from that if we do forget them. Well, if we halve each of the angles here, so I've written here halving 2 theta, well, half of 2 theta is just theta, so we'd end up with an angle that's half the size. Well, it makes sense then that if we follow this formula, here where there's 2 theta, there's thetas in it. So here where there's thetas, we would have theta over 2. And all the way through here, I've got the same thing. Instead of 2 theta, I have theta. And instead of theta, I've got half a theta, or theta on 2. So generating these is really quite straightforward from these ones. We've just got to halve the angles. Well, these next ones, we're going to start with tan. Okay, and that's because the very definition of T is that we're letting T equal tan of theta on 2. Now, what you're going to see here is that this one is nice and easy to understand. We'll write it out formally as a proof, but just let's have a look at these two things. If we've said that T is tan of theta on 2, then clearly what we've got here on the top is 2 lots of T. And what we've got on the bottom is 1 minus T squared, because this is the tan of theta on 2 all squared. So basically this is just a tidying up of this formula where we say, hey, let's let that nasty looking bit tan of theta on 2 equals something nice and simple like T, and it just makes the formula look nice and easy. So this one is really easy to understand because it's the one that everything's generated from. And then we need to know how to prove these ones. Okay, so I've written down the bottom here, all of the T formula are on your reference sheet. So you don't need to memorize them, but you do need to know how to derive them and how to use them. So let's have a look at how to derive each of them first, then we'll look at using them. Okay, we've just done the first proof verbally, but let's set it out nicely in our book now. Let's look at the proof that the tan of theta equals this, where T equals that. All right, well, let's start by just writing out what we know from that double angle formula, that the tan of theta equals 2 tan theta on 2 over 1 minus tan squared theta on 2. And then we just make the substitution. Let's let T equal tan of theta on 2, and we get that tan of theta must be 2t over 1 minus t squared. So that one's really nice and straightforward. Now let's look at the proof that cos theta equals 1 minus t squared over 1 plus t squared, where again t is that exact same thing. Well, let's start with what we know from that double angle formula. Cos theta is equal to cos squared theta on 2 minus sine squared theta on 2. Okay, what can we do next? Well, in the next line, what I've done is I've kind of cheekily just put this over cos squared theta on 2 plus sine squared theta on 2, because I know that if I have cos squared any angle plus sine squared of the same angle, then it equals 1. And so dividing this whole expression by 1 effectively keeps it the same, but puts it into a slightly different looking form. Now for the next step, I'm keeping in mind that I know that sine of any angle divided by the cos of that angle equals the tan of that angle. You don't need to write that down, I'm just thinking that through. Because what I'm going for here is I want some 1s and I want some t's, and remember t is in terms of tan. So looking at what I've got over here, I've got sine squared of an angle. So if I want to turn sine into tan, I need to divide it by cos. But I've got sine squared of an angle, so I need to divide it by the cos squared of that angle. And sure enough, dividing these cos squareds of theta on 2 by cos squared theta on 2 will give me the 1s that I'm looking for. So in any kind of proof, think about how you're going to start. You're going to start each time with the double angle formula. Think about what to do in between, and in this case, it's just a matter of saying, hey, I need it to have something on the bottom. This has only got a top, so how could I give it a bottom that looks sort of similar? And it makes sense here that whatever I've got subtracted, I need to add. And sure enough, that's not changing it because that equals 1. Next, think how you can turn it into this. This is your finish line, and it really gives you direction of where to go. How do I get 1 from cos squared theta on 2? I need to divide all 4 terms by the same thing, cos squared theta on 2. So that will give me 1 here, and here I'll have tan squared theta on 2 all over 1 plus tan squared theta on 2. And I know that tan of theta on 2 is t, so effectively I get 1 minus t squared over 1 plus t squared as required. And what I would put here is dividing all terms by cos squared theta on 2. Now, in a proof, do you need to write these things here? Well, it's not a bad idea because it basically gives you direction of how you knew how to do each step there. So I would write it down now because it reminds you how to do the proof, but later on it'll also just give you that direction. And the proof that sine theta is equal to 2t over 1 plus t squared, where t is that same tan of theta on 2, is really similar. Start by just using that double angle formula. We know that sine theta is 2 sine of theta on 2 cos of theta on 2. Next step is exactly the same as the last proof. We know that the cos squared of any angle plus the sine squared of the same angle equals 1. So let's just turn what wasn't a fraction into a fraction because we can see our finish line here. We know we need a fraction. So we can basically put 1 on the bottom but change the look of this thing. Now, what are we going to do next? Have a look at your finish line. What does it look like? It's got 1 plus t squared there, and we've got cos squared theta on 2 plus sine squared theta on 2. So clearly we need to divide all 3 terms, because this is 1 term, 2 terms, 3 terms. All 3 terms need to be divided by something so that we get what we want. And the thing we need to divide by is clearly cos squared theta on 2, because that will give us a 1 and a tan squared theta on 2, in other words t squared, on the bottom, which is what we're after. So now let's go ahead and make that division, dividing all of this by cos squared theta on 2. One of my cos's down the bottom is going to cancel with this one, and I'm just going to have 2 sine theta on 2 over cos theta on 2. So it's going to give me 2 tan theta on 2 over 1 plus tan squared theta on 2. So writing what I've done here, divide all terms by cos squared theta on 2. And now I'm there. I've got 2t over 1 plus t squared, because I know that, and I should have written this on the last one, where t equals tan of theta on 2. So I mentioned that the t formulae are on your reference sheet, so you don't need to memorize them. You do need to know how to derive and prove them and to use them though. So this isn't strictly essential, but for those of you who are really visual learners, you might like to think of the t formulae using this triangle because you can really clearly see here what the relationships are. You've got the sine of theta being opposite over hypotenuse. You can see the cos is adjacent over hypotenuse and the tan of theta opposite over adjacent. And I think before we had to memorize these on a reference sheet, this was kind of a handy way to look at it. But even still, it puts some of it into a different perspective, I think.